Good morning. Today we're going to combine two lessons, lessons 35 and 36. The first will be some more ideas on the Gram-Schmidt orthogonalization process, and the second will go over the adjoint of a linear operator. At least we'll start by introducing some of the ideas. So let's begin with the recap from the last lesson. So there really we had theorems 6.3, 6.4, and 6.5, so we'll combine it in the following way. Let's say that V is an n-dimensional vector space either over the real numbers or over the complex numbers, and let's fix an inner product which we'll denote using these angle brackets. Right. So I'm going to state three things here. Number one, let's let W be the span of a linearly independent subset and let's call this S, and we'll say that the elements are these lowercase w. Now I'm going to define a new subset which we'll call here S prime, which are right in terms of these V's. And we'll define these in a recursive way. So my VI's are one of two possibilities. Either it's W1, if we start with I is equal to 1, or I'll take Wi here, and then I'm going to subtract away these vectors. So here's Wi inner product with Vj divided by Vj inner product with itself. And of course, this is for all the other i's. And I do want to point out here that these ratios actually are scalars. Right, so again, that's Wi inner product with Vj divided by Vj inner product with itself. So then the statement is S prime is an orthogonal set of non-zero vectors. Moreover, S prime is the basis for W. So that is, it's not only a spanning set, but it's a linearly independent set. And each element Y in W can be uniquely expressed in the following form. So here I have a sum, I goes from 1 to k, and then here I have inner product y with vi divided by inner product vi with itself times vi. And just like before, these ratios here are also scalars. here's a block. So again, this is our first result. If I start with the spanning set, with the linearly independent set, S, then I can construct this S prime. So that really leads into what's called the Gram-Schmidt orthogonalization process. So if we're given a basis S for a space W, then we can construct an orthonormal basis as follows. And I'll call this S double prime. So step number one is we'll construct these V's as above. And then step number two, we'll construct the U sub I as we take the inner product of VI with itself, and then we'll divide by the square root of that. So again, I've told you how to start with the WI's, I construct the VI's, then I construct the UI's. So of course this here is now an orthonormal basis. Now, before I get too far in all of this general theory, I really want to ask a very simple motivating question. And simply put, what's happening with the geometry here? Right, so we've written all of this, but there should be some pictures that we can draw. So I'm going to go over this motivating example. So remember that we can do the following trick. Let's let V be R2. And let's let our inner product be the standard inner product. Now we saw before that there are infinitely many orthonormal bases. So to remind you, let's fix two real numbers A and B, not both 0. And let's define this orthonormal basis let's call this beta in terms of U1, U2, where remember U1 will be this vector AB, but then we'll normalize it. And we have our vector U2, which really is the vector minus BA, but again, we'll normalize it. Okay. So what I want to do here is consider now the span of these two vectors. fact, I want to consider the spans separately. So W, I will let this be the span of U2, and W, with this weird looking symbol here, I'll let this be the span of U1. Right. So this here, I will call W perp. Right, and I'll explain in just a minute why I'm actually calling this W perp. So first of all, if I take a look at the span of U2, right, U2 is this vector here, then really this has a nice geometric interpretation. This is the set of vectors in our space such that AX plus BY equals 0. Right, so we discussed this kind of towards the beginning of the class. Similarly for U1, this has a nice geometric interpretation. This is the set of vectors such that BX minus AY equals 0. So here, we can try to plot these out to get a better idea of how this looks. So the whole board here will be R2. We have our x-axis, we have our y-axis. So W is this line here, AX plus BY equals 0. And I can really think of that as here has some direction U2, and I just want to take a look at kind of everything here along this direction. Similarly, we can take a look at this so-called W perp, and this was our BX minus AY equals 0. And of course, we know that this here has to correspond to this vector U1. These here are going to be perpendicular to each other. That's exactly where this perp here comes from. The perp really means W perpendicular. Right, so I have this line W, and then I have this perpendicular line W perp. Right. Now, we have a claim that says any vector can be written as linear combinations of U1 and U2. Well, for that claim, actually I'm going to use this expression here. Notice that I had this y looks like this here. So what I mean by that is any v I can write as the sum here. So this notation will look a little bit weird, but I'll write it this way. I can write v as the sum of these two, where the first one here, I'm just going to use this notation here. So here I want to take the inner product of v with u1 divided by u1, u1. And then this here, I'll take the inner product of v and u2 divided by inner product of u2 and u2 times u2. Right, so again, for this claim here, I'm just telling you what I mean by these weird looking symbols. I can write it as the sum of these two, where now I'm just using this proposition here. So if we stare at this for a little bit, and if you just work out the formulas, so if my vector v looks like maybe x comma y, I have my u2, which is this thing here, and if you just multiply everything out, then for this so-called v parallel, I would get ay minus bx over a squared plus b squared times this vector here. And for the second one, I would just get ax plus by over a squared plus b squared times this vector here. So again, I can take any vector, xy, and I can write it now as the sum of these two vectors. But this here is on one line, this here is on the other line. Right? In fact, this here is on the line w, and this here is on the line w perpendicular. So this here, this v perp, means that it's actually on the line perpendicular, whereas this here, v parallel, actually means that it's on the line. Right, here I'll write perpendicular to w. Okay. So of course, if you just wanted to kind of see a picture, it says something like this. Let's say perhaps if I'm out here at this v, then I just have to move over a certain amount this way. This might be my v parallel, and then I should move up a certain amount this way. This is my v perpendicular. Right, so to get to any point here, I just have to move over a certain amount this way, and then move up a certain amount this way. Right. So here's maybe one observation to make. Given any point in the plane, how close does it get to a line? So again, given any point, how close does it get to a line? Well, you can actually see by how close it gets, I really mean something like this here. Right? If I have a point here, then this length better be the closest that it gets to this line. Right? Because if I kind of take a point here in this line, it doesn't really get that close. I take a point down here, it doesn't really get that close. But if I move in kind of here in the middle, this point here is kind of the closest that I will get to this line. So it's close kind of in the sense of the picture here. Right, so this point here should be close because this point here is far away, this point here is far away, but this point on the line should tell me how close it gets. So simply put, the answer should be the norm of v parallel. Saying this right. And if you work this out, sorry, it should be the norm of v perpendicular, ax plus by over this here. Right, because again, I'm just taking the norm of v perp, and it should be this here. So we're going to try to generalize a lot of these. So again, there's a couple of different things that are happening here. If I have a vector space, and if I look at the inner product, the standard inner product, I will use an orthonormal basis to try to make sense of the geometry here. And I want to try to answer questions like this here. Like, how close do we get to a line? And that's really in terms of the geometry. Right, so let's try to do something a bit more general. So first, let me try to make a bit more sense in terms of this W perp. So I want to get into what's called the orthogonal complement. So just like always, let's say that V is an n-dimensional vector space over either the real numbers or the complex numbers. And let's fix an inner product. Okay. Given a subset S, we'll define its orthogonal complement as the following subset. So this here will be the set of vectors such that this inner product is 0 for all y in S. So this here is exactly this picture up here. So the way to think of this is, if I have my W, which is a line, W perp will just be the line orthogonal to that. But it's not any different from the picture that's here. So with this here, we have the following theorems. So 6, 6, 6, 7. So this says, let's let W be a subspace of V. Right, so before I just said this for an arbitrary subset, but now let's do this for a subspace. So the first statement is that W perp is also a subspace. Number 2, the intersection is just the origin. Number 3, for each y, there exists unique I'll say here U and W and Z and W perp such that y is U plus Z. Moreover, the vector U is the unique vector in W that is the closest to Y. Really what I mean by that is this. For any x in W, we have the following inequality. So the distance from x to y is greater than or equal to the distance from y to u. Right? Now I'll try to say a little bit more in terms of the picture over here, but again, the whole idea here is that if I take any point x along the line, then it doesn't get any closer than where I would be here at u. Right? Then let me state the fourth result here. And it says that the dimension of W plus the dimension of W perp is the dimension of V. Okay, so let me try to explain a little bit of what's happening here in the sense of this motivating example. Let's say that V is R2 and W is the line AX plus BY equals 0. All right, so just like before. All right, so I'll just redraw this picture over here. So here's our line W, and then we know that W perp looks like this here, right? So it's 90 degrees apart. Okay. So first of all, you'll see that that intersects, these two lines intersect in exactly one point. Right? The point of intersection here is the origin. So that's what statement number 2 says, right? So they always intersect in exactly one point. Number 3, given any V we can write this here as U plus Z, where U is what I was calling here as V parallel, and Z is what I was calling here V perp. Right? So again, in terms of a picture, if this is my V, I can move over so far here for U, and then I move up so far here for Z. So if I had any other x here, so let me write this as any other W in W, then the distance here between V and W is greater than or equal to the distance here between V and U. But of course, that distance there is exactly what we're calling here this ax plus by over the square root. Right? So again, the distance here is never less than this distance here. So this is the closest that we get. Right. Finally, you can see what's happening here with the dimensions. Well, the whole space here is two-dimensional. And here I have the line, which has dimension 1, and the perpendicular line, which has dimension 1. So this here just says 1 plus 1 equals 2. So again, this picture here really exemplifies what will happen in a very general case. Now we can use all of this actually to make a definition. And I want to explain where this definition comes from by more or less trying to sketch how would you prove this last statement here. So let's do the following. All right, so again, I want to try to sketch at least the proof for the last statement and use this to motivate a definition. Well, our W here has a basis. So theorem 6.5 asserts that this subspace W here, this has an orthonormal basis. Let's call this S double prime, which consists of these vectors u1 through u sub k. So let's make the following definition. Given y and v, let's define two things. Let's define u which I'm going to write here as proj subscript w of y to be the following sum. So here I'm going to take the inner product of y and ui times ui. So remember that these here are scalars. And then let's define z as y minus u. Okay, so again, given a y, I'll make these two definitions here. So with this here, one can show that u is in W. Of course, it has to be in W because this here is just a linear combination in terms of the vectors of S double prime, but S double prime is the basis for W, so U better be here. And the trickier part is that Z is actually in W perp. Right, so that's not easy to show. That takes a little bit. Right, but we have this here. And so at least this explains where this part here is coming from. Right, so why we have this. Now let me keep going a little bit to kind of explain more what's happening here. In fact, now, we have a linear transformation this proj sub W going from V to V. So what this does is it'll take a Y here and it sends that to this sum. Right, so again, this here is a linear transformation, and one shows that the range of such a transformation is W, and the null space of such a transformation is W perp. So again, the range is W. The reason being, if I have an element over here, that is exactly in the span of S double prime. But the span of S double prime is exactly what we're calling W. And then the hard part is to show that the elements that map to 0, that is what's in the null space, are exactly those that are perpendicular. Now, let me perhaps redo this here in terms of this example that we did back over here. So So as a specific example, let's say, just like before, that V is R2, and W here is this line, AX plus BY equals 0. Well, remember that we already have a vector here. W has this basis S double prime, where this U2 is now this vector. Let's see, be careful we're saying this right. So once we have this, then we make the following definition. This proj goes from R2 to R2, and it'll take a vector xy. And now I want to send this to what I'm calling V parallel. And remember that V parallel, we worked out a formula for this. It's given by this here. Right? V parallel, of course, just like before, we were calling U. So let's try to draw a picture to see what is this actually telling us. So here's X, here's Y. Let's say this here again is our line W. This here is our line W perp. And so what we're doing here is if we have a vector V, then we know that this vector we can write as V parallel and V perpendicular. So what proj W it does is it projects onto the line W. So quite literally, it's like it's shining a light like this here. So if I'm sitting here at V, when I shine this light, then of course the shadow here is V parallel. So again, V parallel looks like the shadow here after I shine this perpendicular. Also, you'll see that V perp has no shadow. Right? In fact, everything here on W perp, when I shine it, I don't see anything at all. Right? Everything here on W perp kind of shines down here to the origin. But that's exactly what it means to say that it's in the null space. Once I shine the light on W perp, there is no shadow. So this is the idea of this proj map, is that it tells us kind of when we see W, and then more or less it ignores everything on W perp. So again, these are the two properties. The range of this projection map is W. The null space of this projection map is W perp. Right? And the projection map is defined exactly in this way here once we have an orthonormal basis. So now what we'll do from here is continue to play around with the inner products, but now we want to know, how do linear transformations behave with respect to inner products? Right, so I'll write that very vague question here. How do linear transformations say t going from v to v behave with respect to inner products? And of course, this is being very vague, but this is what we want to focus on. So this here leads to what's called the adjoint of a linear transformation. So to this effect, just like always, we're going to say that V is a vector space over either the real numbers or the complex numbers. And just like before, we'll fix an inner product. Okay. So there's two theorems here, 6.8 and 6.9, that are all related to a linear transformation. So first of all, let's say that for each y in V, let's let G be that map that sends X and V to this inner product, XY and F. Right, so again, G is a map that takes a vector X and it returns back the scalar inner product X and Y. So the statement is that this is a linear transformation. Right, I want to say something a bit stronger than this. Conversely, let's say that G, so notice now that this is going from V to F, right? Not V to V, but V to F. Let's say that this here is a linear transformation. Then there exists a unique Y such that G of X is this inner product of X and Y. So every linear transformation from V to F, right, not V to V, but V to F, in this case, is uniquely determined by this element y. Right? And I'll try to give an example in just a minute. Second statement, let T be a linear transformation then there exists a unique transformation which I will call T star such that if I were to take the inner product of Tx and y, that's the same as the inner product of x and T star of y. So in other words, I can kind of move the T from one side to the other, but I have to be careful that it might change just a little bit. Okay, so the point is that we have to see properties of this to see what's happening. I should say, see examples of this to see what's happening, and then to also see why this works. So first, let me try to explain what's happening here for the first part. Well, let's say that V is Fn, and we have the inner product so this is R1, X1, Y1 bar, R2, X2, Y2 bar, Rn, Xn, Yn bar. Okay. So now, if we have any linear transformation, let's call it G, that has to be in the following form. So G of x here looks like maybe C1, X1, C2, X2, Cn, Xn. Right, because it's a linear transformation, so I have to write it out like this way here. And of course, this here I can write in this way here, where I can tell you what y is. So y1, this is just a matter of kind of matching up these two things here. So this here would just look like, let's say here, 1 over r1, the conjugate here of c1, y2, look like 1 over r2, the conjugate of c2, and then yn here looks like 1 over rn, the conjugate of Cn. So again, if I have a linear transformation, then I know exactly what it looks like here because I can tell you exactly what y is. So this is why if I have a linear transformation on Fn, then I can tell you what the y is, like in this sense here. There has to be a unique y. So really, morally, it's saying that every linear transformation from V to F is basically nothing more than an inner product. Right? So again, morally it says every linear transformation from V to F looks like it's an inner product. Now if we keep going, so again, let's say that we have this here. And now let's say that we have a linear transformation. call this T. This is in the following form. Any linear transformation from V to V is in the following form. So T here, of course, has to take some vector x1 through xn. And now notice that we're going to have a matrix. So if you will, you can call this here your matrix A. And so if you just played around with things, then much in the same way here, once you take a look at the inner product of T of x and y, then you kind of use this formula here. You see that you'll have something in terms of x. And in this case, your T star will almost look the same as what's here. But now I have to do a trick that looks something like this. And here what will happen is I'll have a 1 over R1, A11 conjugate, 1 over R2, A21 conjugate. Sorry, it should be R1, 1 over R1, AN1 conjugate, 1 over Rn, A1n conjugate, 1 over Rn, A2n conjugate, 1 over Rn, ANn conjugate. And this here is morally, if I kind of ignore the r's, this looks like the transpose of the complex conjugate of A. Now I want to emphasize here, looks like, so I have to be careful as to what these scalars are here, depending on the inner product. So this here is what we call the adjoint of T. And of course, really the goal is to understand this more. So I want to emphasize that this is not the same as the classical adjoint of a matrix. So of course, we'll come back and then we'll study this idea here in a lot more detail in the next lesson. All right, so thanks for listening.